Bonjour tout le monde, bonjour Monsieur Fanshuo Ma. Je me présente, je suis le président de ce jury. Je suis Riccardo Artoni, directeur de recherche à l'Université Gustave Eiffel. Et je vous présente en votre jury les rapporteurs Pascale Aussillous, Vincent Richefeu, les examinateurs par moi-même, Eiffel. Vous connaissez aussi les invités, M. Farangatiaï, M. Jean-Noël, puis il y a aussi dans le jury vos encadrants, Pierre-Yves et Gustave. Voilà. C'est à vous.
Okay.
De défendre votre thèse.
Okay, thank you, the opening of the president, and also thank you everyone for coming. I will present my work during my PhD carried out at Institut dans le Rond d'Alembert under the supervision of Madame Lévis-Taron and Monsieur Pierre-Yves. In our work, we are interested in the cohesive granular materials and its structure, flow, and the quantitative laws. The granular material is everywhere around us, from the coffee grains we consume every day in the lab to the piles of granular materials, construction materials we can see on the street. It can form the desert of 1,000 kilometers square. And if you look up in space, we have the ring of Saturn. Basically, it is also the granular composed of ice. It is also highly concerned in industrial process, and it is reported that the sun is the second most used resource on Earth, just after water. In physics, according to Monsieur Dejean, the granular matter refers to the particle system in which the size is larger than 1 micron. And we consider here the particles are rigid. Effectively, the interaction of a particle system may depend strongly on the particle size. For the particles smaller than 1 micrometer, we have the thermal Brownian motion pronounced. And for larger particles such as the powder, the clay powder, and the floor particles, we have the adhesive attract interactions such as the van der Waals force and electrostatic force. And for even larger particles, as I showed in this picture, we have the contact force such as the friction and the repulsive force. And also, we cannot neglect the weight of the particles. In terms of macroscopic behaviors, one important feature of a granular material is that it can flow. It can behave like a solid, gas, or liquid according to the external condition. Here, I show a very classical example: the flow of a beads over an inclined plane, over a sand pile. From the top to the bottom, we can see the gas behave like a gas, highly agitated, and in the middle, they rearrange and move as a liquid, and the bottom, they form as a solid, and the shape doesn't change. Naturally, we can ask the question, what would happen if we introduce the adhesive force? First, let's talk about where may the sticky grains come from. Just like I said, we have the van der Waals force and intermolecular attraction between the particles. But the amplitude of this van der Waals force may decrease dramatically as the size of particle increase. And another more common mechanism to introduce adhesive force is the capillary force, due to the presence of a capillary bridge between the particles. We can parameterize the function of the capillary force by the surface tension, the radius of the grains, and the geometry of the capillary bridge. And more recently, we have Gans et al. They fabricate the adhesive beads by enrobing the spherical beads by polymer coating. In this way, we can fabricate a temperature-independent cohesive system. And also, we have a homogeneous adhesive contact network. In our work, we characterize the local adhesive strength by the granular bond number. It is a non-dimensional number, compare the adhesive force to the weight of the particles. In the terms of macroscopic behavior, if we take solid sand piles, due to the presence of the adhesive force, we can see the increase of the repulse angle due to the presence of adhesive force, which coincides with the increase of yield shear stress. And for the granular flows over an inclined plane, as we increase the adhesive strength of between the particles, we can firstly notice that the maximum velocity that the flow can reach decrease as adhesive force increase. And also, a plug region where zero velocity shear can happen and can appear. Also, Debov et al. They observed that for the free surface of a cohesive flow, the free surface becomes more rougher due to the adhesive force. And we characterize a macroscopic cohesive level by the cohesive stress dossi. We note here dossi. Based on the previous phenomenological observation, our work is motivated by the following question. First is how we can characterize the gravity-driven failure onset of a cohesive system. And is there a rheological law can capture the kinematic aspects of a cohesive flow or an inclined line, and how we can relate it to the macroscopic cohesive stress to the local adhesive strength. Finally, what is the application of the local adhesive force to the free surface stiffness? For the rest of this presentation, I will develop my work as following. First, I will introduce our numerical method, and followed by two parts addressing the mechanical behavior of cohesive gradual material at the solid regime and fluid regime. And finally, conclusion and perspective are given at the end. We use discrete simulation method in our work, namely contact dynamic method. Unlike another method, namely molecular dynamics, in our work, in our method, the particle overlap does not enter into the contact model, and the contact force are resolved with implicit solve law. For instance, we use classical Sunio-Hini contact law. It gives all the admissible normal contact force. It states that a positive normal contact force only exists when the contact velocity is 0. And the bounded Coulombic friction law gives all the admissible tangential contact force. And you may notice here, these two contact laws, they give infinite number of the admissible force. So we need to select the force which are compatible with the dynamic equations. Here I illustrate the idea, use a frontal collision problem. At instant t, at the beginning of the time step, we detect a contact between two particles. At the end of the time step, the contact opens. Writing the conservation of moment equation on the contact frame, we can relate the normal contact force to the variation of a relative velocity. But please note that we cannot use this equation to decide directly the contact force, because in our problem, the relative velocity after the time step is still an unknown. So the contact dynamic method, he defined a weighted contact velocity, combine the pre and post relative velocity and weighted by a normal restitution number. If we inject the second equation to the first equation, we can relate the normal contact force to the normal contact velocity, and it is an affine function. Similarly, we can relate the tangential contact force to the tangential contact velocity. If we plot these two affine functions to our contact law, then the intersection with the contact law gives us the contact force. For instance, for the normal contact force, if we have RNEG is positive, then we have positive contact force. If RNEG is smaller than 0, then the normal contact force is 0. To introduce the addition force in our contact, we shift the Sunio-Hini graph to the negative value to allow the negative force to be selected. Besides, we defined a rupture length allows the adhesive contact to persist even when the physical contact opens. In reality, we deal with a multi-contact problem. The solution of the force is similar. Just when we write down the conservation equation, we should consider all the other contacts with the particle ing. And as a result, we should incorporate all the contact force with particle ing to the coefficient ing and RTEG. And finally, the solution of the contact networks is converged with Gauss-Seidel iteration method. So in the first part of our work, we try to explore the gravity-driven failure onset of a cohesive step. Here, I show the initial state of our numerical configurations. The system initial state is constrained by a right-hand vertical wall. Once we remove the right-hand wall, the system began to evolve and collapse under the gravity. Here, some relevant system parameter is shown here. We recall that we resolve the normal contact force with a shift Sunio-Hini graph, where the NC characterizes the maximum value of the adhesive force, and NC equals to bond mg. Besides, we have three initial states by changing the different distribution of the particle size to prove the reproducibility of the measurement results. Here I show different snapshots of the system taken at different time, and the particles with velocity larger than the system mean value is colored in black, and for the rest of the particles, a linear color scale is set. At the very beginning of the system, we can see that no evident deformation happened, but the system presents a uniform velocity distribution that proved the existence of the diffusion motion. And in the course of time, the localized green happened on the right upper corner of the system, coincide with the particles which are higher system velocity than the mean value. At the end of the system, the system returns to the static state, and the diffusion motion appears again due to the rearrangement of the particles. So from here, we observe that the diffusion motion in the course of the system evolution, the diffuse motion and the localized motion coexist. If we want to establish a displacement-based criteria to detect the failure onset, we should the displacement threshold, capital RTH, to distinguish them. Before we developed the analysis, I will show here some definition. We would use it later. First, we called the mobilized grains is the grains whose cumulative displacement exceeds capital RTH. And the NTHD is a function of time. It describes the number of grains whose displacements exceed a certain value. We note here the small RTH. If we take a system of height 60 diameter grain and bond equals to 50, we plot the evolution of the NTH in the course of time with different applied small RTH. You can notice that the NTH increased dramatically at the beginning, means the system is mobilized, and at the end of a certain time, the system relaxed and the value of NTH saturates to a certain value. Of course, another highlight to note is that the NTH decreases systematically as we increase the value of RTH. That means the particles, there are less particles that exceed a larger displacement. If we plot the NTH at the end of the system in the function of all the small RTH we used, there are 2 points we can highlight from this curve. Firstly, is the dramatic decrease at the beginning of the system. That shows that the particles with small displacement is rather sensitive to the increase of RTH. And after a smooth transition, the curve converges, saturates, and converges to a constant value around 1 diameter grains. That shows that the particle who displaced over 1 diameter grain has more chance to develop the failure. If we exacerbate this curve and choose vertically the value where all the diffusion motion disappeared, we can have the capital RTH equal to 0.15 d as the displacement threshold to discriminate the diffusion motion and the localized motion. With this threshold defined, we can characterize the chronology of the system failure. Again, I will give some definition about the value we would use. First, we call the delta NTH is the increment rate of the mobilized grains number at instant t. At the delta NTH max is the maximum value that the delta NTH can reach during the evolution. And the dot z is the instant when delta NTH undergoes a decrease of 0% of delta NTH max. We take the same system with height 60 diameter grain, and always we take bond equals to 50. We can plot the curve of the delta NTH in the course of time. Short after the system starts, we have the delta NTH reach the maximum value at dot 0, and the surge of this evolution of this curve is after short. That means that after a short time, the system stabilized, and no more new grains can exist. No more new grains are mobilized. If we plot the mobilized grains at different instants, we can find that the mobilized grain located on the right upper corner of the system form a linear failure plane with the system. But which instant is the most appropriate to characterize the failure onset in the system? We may think that the dot 0 is the best candidate because at this specific moment we have the maximum number of grains get mobilized. If we plot, the variation of the failure plane between 0 and -t, we can note that it is almost a constant. Failure angle doesn't change much during this time. And if we calculate the error of the fitting, we can notice that it is decreasing, always decreased in the time. The objective is to find a tau z where the system the failure haven't developed too much, and also we won't have a better fitting quality. So we find tau 75 to characterize the instant of the failure onset. If we plot the failure onset moment, and if we compare the failure onset moment with the evolution of the system mean velocity, we can find that according to our criteria, the failure occurs at early stage of the system collapse. Then at tau 75, we plot the failure angle alpha. We note this as alpha. For the next, we applied our criteria to the system with different height. We noticed that the failure angle alpha is decreased systematically as we have a larger system. This result is qualitatively consistent with the experimental measurements. In fact, the objective that we measure the alpha angle in the function of height is we want to investigate the addition, the relationship between the addition and the internal friction angle. But before doing that, we need to test the reliability of our criteria. As you can see, all the criteria is established by taking a unique system with a unique height. It is reasonable to wonder if we can do that for the system with different height. So we test the reliability of our criteria on the system weight. Here we plot the distribution, the displacement distribution of the system with different height, and we found that the capital RTH effect is highly sensitive to the system height. If we plot the failure angle using different criteria found with different height, we find that it's rather a large dispersion shown in the measurements. But the dispersion shown in the data due to the different criteria is smaller than the dispersion of the measurement due to different choice of the initial state. So we can give some middle point conclusion for this part, is that we discussed the possibility of a displacement-based criteria to detect the failure onset, and we found that the reliability of this criteria is highly challenged by the granular disorder nature, because when we use the initial system with different particle size distribution, we can find the dispersion in the data is higher than the distribution when we use different criteria. Finally, the distribution due to initial state is less pronounced for larger systems. So in the second part of my work, we're interested in the granular flows over inclined plane. Here I show two examples of the cohesive granular flow in the nature. One is a mass just detached from the mountain, and a cohesive flow is initiating. And other one is a snow avalanche along the mountain. We can see the roughness motif form on the free surface. So three questions we want to address in this part. We want to discuss rheology to capture the kinematic aspect of the cohesive flow. And we want to relate the macroscopic cohesion strength τ to the local adhesion strength characterized by the bond number. And we also study the free surface roughness. So I show here the numerical setup we're going to use in this work. And for this part of work, we focus on the steady uniform state of the flow. And remember that the normal contact force is solved with the shifted Sinuhini graph, and the maximum adhesive strength is characterized by the NC equal to bond mg. Besides, we set a really small rupture length to stabilize the adhesive contact. As we can see here, we have just seen a movie of the flow over inclined plane. We want to know we can predict the velocity. It means how we can predict the kinematics of the dry granular flows. We have the pioneer work of Bagnol lead to a classical Bagnol velocity profile. And more advanced in the understanding of the dry granular rheology is the mu-I rheology. It states that the friction in the granular flow can be described by Coulombian friction law, τ equals to the mu-I multiplied by the normal strength. And the friction coefficient mu is a function dependent only on the initial number. Here I show the definition of the initial number. And through the numerical and experimental measurements, we can find that the mu-I can be described by an affine function depending only on the initial number. So the first idea is to verify through our numerical method if we can reproduce this friction law. So first, for a uniform steady flow, for a dry uniform steady flow, we have at each depth in the flow, we have a mu-I equals to the tangent theta. And if we plot the profile of the initial number for the flow with a different slope angle, we can find effectively the I is a constant in the packing of the flow, besides accept the two boundary region. If we plot the mu I given by the tangent data in the function of the inertial number, we can effectively find a linear friction law verified by our discrete numerical simulations. From this linear friction law, we can calibrate these two frictional parameters. Another way to verify our numeric method is we can derive the velocity profile for a flow over an inclined plane. And here I recall simply the procedure to find the velocity profile of for a flow over an inclined plane. We can find in the expression of the velocity profile, it indeed depends on the two frictional parameters we just calibrated from our discrete simulation result. If we compare our numerical simulations to the theoretical solution, we can find that rather good agreements can be obtained. And the question is that what's the role of the cohesion in this problem? For modeling the cohesive granular flow, we describe this material, we describe the granular base cohesive contact model, saying that the shear stress is a linear combination of the Colombian friction and the macroscopic cohesive stress. And at this stage, we assume the independence between the cohesion and the addition. These 2 points, we will verify it later with our simulation results. And for a steady uniform flow, we have a shear stress and the normal stress compensate the projection of the gravity over the inclined plane. And we can relate the tangent data to the friction coefficient and the dou. Starting from this equation, we can find the velocity shear. It should be noted that there exists a critical height at where the velocity shear equals to 0. And if we integrate the velocity shear, we can obtain the complete velocity profile. But please note that the modeling of this cohesive granular flow depends on two assumptions. One is a linear rheological model, and the second is the independence between the addition and cohesion. And now we would verify these two assumptions with our simulations. The first point consists in verifying the linear rheological model. So if we take a flow with a certain bond number, and we have the uniform steady flow can be established on different slope angle of different slope angle. Then given an initial number, we have a different position at where this initial number can be reached. This allows us to plot the shear stress in the function of the normal stress. We can find that in this curve, the gradient, in fact, it gives the friction coefficient, and this intersection point gives the dou. So we have proved that the shear stress, in fact, is an affine function depending on the normal stress, from where we can verify our first assumption of the modeling. The next point consists in verifying the independence between the friction and addition. If I repeat what we have did for one single bond number, we repeat the thing. We take the flow with different bond number, then we can plot the friction coefficient mu given here by this bond in the function of the inertial number. We can find that the data of a different bond number it collapses on the same figure, which we obtain by the calibration using the non-cohesive flow. And in the similar way, we can plot the dou in the function of the initial number using a different bond number. And we can find that the independence between the friction and the cohesion is acceptable. Once these two assumptions have verified, then the velocity profile is solely depends solely on the macroscopic cohesive stress. This allows us to investigate the relationship between the macroscopic cohesive stress dou and the local adhesive stress bond. So here I show the theoretical prediction of the maximum velocity Umax. We can say that it's depending only on the dou. So for a certain flow, for a certain simulation, discrete simulation, we can match this theoretical prediction to our simulation result to get the relationship between the dou and bond. And on the same graph, we plot the result of the local measurements, we can see that the two results are consistent. If we take this linear dependency to our theoretical prediction and compare with the full velocity profile of a discrete simulation, we can see that the velocity profile, they show a rather good agreement. Yes. And another way to investigate the relation between dossier and bond is by measuring the plug thickness. Effectively, if we take the expression of a velocity shear and set it to 0, we can get the thickness, theoretical thickness of the plug flow. And this thickness, it depends on dossier. And in our experiments, we characterize a distance by bond. So if we compare this theoretical prediction to our numerical measurement, we can get another measurement for the dossier and bond. If we take a velocity field of the numerical simulation, we can say effectively there is a region where velocity shear equals to 0. But the interface between the plug flow and the shear flow is not sharply defined. So we need a cutoff value for the relative variation of velocity to conduct the measurements. In this figure, we plot the relative variation in the function of the position for a couple of flow with different bond and theta. Effectively, for a rather small value of theta v, no evident change in the position. And starting from 0.01, the YC increase importantly. That's because we enter to the flow region, into the flow region. If we take the critical cutoff value for the relative variation of velocity, we can measure the thickness of the plug region for flows with different bond number and theta angle. It's shown here. And due to this equation, we can find just what we did for the using the Umax. We can find a linear relationship between the dossier and bond. And also by changing the critical cutoff value, we show that the effect is marginal for the small number of bonds, but the dispersancy increased for a large bond number. Also in this figure, we regrouped all the measurements relating the dossier to the bond using different measurements, including the Umax, the thickness of the plug, and the local measurements. We find a rather consistent result can be found. If we take the linear dependency, take it back to the analytical solution, and we plot the curve compared to the discrete measurement of the results, we can also find a consistent result in terms of the thickness of the plug region. And next, we try to describe the roughness of the free surface. Here, the roughness is simply characterized by the profile fluctuation compared to the mean value. If we plot the power density function of this fluctuation, we can find it can be well fitted by a Gaussian distribution function, from where we can use the classical statistical parameter, the standard deviation, to characterize the fluctuation, because a larger band means a larger deviation, standard deviation, and a larger and a rougher surface. Here we plot the standard deviation for the flow of established on different hill angle and different bond number. We can find that for cohesive flows, a larger bond number can induce a higher standard deviation, and that means a larger bond can induce a rougher surface. And here I can drive some conclusion of the second part. So during the second part, we try to propose a single real-logical model using the classical definition of the inertial number I, and we test it with our numerical results. And from this real-logical model, we can describe analytically the kinematic aspects of the flow, such as the maximum velocity and the thickness of the plug. And the theoretical result allows to measure the system macroscopic cohesive stress in the function of the local adhesive stress, and consistent results are obtained. And following this conclusion, we can propose two perspectives. One is, can we relate quantitatively the system cohesion to contact adhesion, and we can try to implement this simple rheological law to a continuum numerical framework, numerical simulation framework. So for the second point of the perspective, we use the 7-node multi-layer solver in Basilisk. Here I recall briefly the simplification we used to arrive to the system we're going to solve. First, we took the full 2D Navier-Stokes equations and we applied the thin layer approximation, seeing that the variation in the longitudinal direction is much larger than the variation in the transverse direction. And we can obtain the reduced Navier-Stokes Planck equations. And then we integrate it over the fraction of the height to obtain the system of equation we have to solve. Here, the alpha is a factor of the profile. It is legitimate to take it to equal to 1 if we have a thin layer in the system. And the blue term, in fact, is the difference of shear stress between the upper and the lower interface of one layer. Here, according to different flow we considered, we can write the expression of the shear stress according to the rheology law. Here, we're going to test if we can implement this rheology, locally defined rheology in this multi-layer solver. So the effective viscosity can be written as the following according to the different rheology of the flows. And the diffusion problem can be solved by these equations. And if we rearrange the different terms, we can arrive to an equation which we can write it in the matrix form. And this matrix form can be solved by Thomas algorithm. Here I show a simple test case. I implement the granular flow mu-I rheology into this multi-layer solver. Here I show the flow established on different Taylor angle. We can find a good agreement between the numerical simulations and the theoretical prediction. If we define the maximum error between the numerical solution and the theoretical one, we can find the error decrease when they increase the number of layers. Another point in the perspective is that, as we have shown good consistent between the Dorsey, good qualitative relationship between the Dorsey and bond, how we can predict it with a good qualitative arguments. In fact, the things is still elusive because in the simulation methods such as DEM, the molecular dynamic method, the expression of the additive force may depend on different parameters. It may depend on different additive model we use. It may also depend on the damping friction or the stiffness value of the particles. And in quantitative methods, as the additive force is determined implicitly, it seems that we can avoid these troubles due to the numerous model for the additive force. But in our problem, the additive force may depend on time step. I will explain why. If we retake the example, the frontal contact problem I introduced at the beginning, if we have the NEG is smaller than the lower limit NC, then in fact we impose the additive contact force. And in this case, the numerical time step cannot be cancelled out from the dynamic equations, which means that the variation of the contact velocity, in fact, it depends on the numerical time step. If the variation of the contact velocity, it would decrease if we have a larger numerical time step. That means an increasing effective cohesion as we increase the delta t. Here I show the system mean velocity in the function of delta t. We can see that effectively the system mean velocity it decreases as we increase the numerical time step. We try to remove this effect on depending on the time step by implement a semi-implicit approach to remove the effect of time step, as we assume that the dependence on delta t comes from the lower limit we set in the Sinuhe graph. So we propose to solve the normal contact force with the classical Sinuhe graph, and we can see that the dynamic equation can be independent of the delta t. And we treat the additive force as a abortive force, just like gravity. That means that we reduce this NC from the resultant force of each grain in the contact. And we plot the mean velocity computed by the semi-implicit method. We show that in the semi-implicit algorithm, if the dependence on time step still persists, that means that the reason why our result depending on time step does not come from the shift we did to the Signor-Gini graph. And we think that the reason why we have time delta t persists is because we have the coarse graining effect. But what we also find that I didn't show in this slide is that we can get a better numerical efficiency for the semi-implicit algorithm. So at the end of this presentation, we asked some questions, and now we try to answer them. So how we can characterize the gravity-driven failure onset is that we discussed the possibility of a displacement-based criteria to detect the failure onset, but we meet the inherent difficulty due to the disordered system, due to the non-homogeneous system that we have here. And a good agreement between the theoretical modeling and the numerical simulation motivate us to implement it in more effective continuous simulations. And how the macroscopic equation may depend on the additive strength, we got a consistent linear relationship, a consistent qualitative linear relationships irrespective of the kinematics. And we found that the additive force carries the signature of the cavity strength from investigating the free surface roughness. More work should be done in the future. We need to explore more about the semi-implicit algorithm and the implicit algorithm to better understand the effect of time step. And we may study the slipping velocity bring for different bottom surface and try to implement it in continuum simulations. And finally, we can try to use a continuum simulation to model the front of a cohesive avalanche. Yes, thank you. Merci pour votre attention.